Okay, good morning, lads and ladies. Welcome back. I guess one thing you'll notice right away is that I have pretty much lost my voice. I'm going to do my best to get us through class here today, but I'll ask that you bear with me. There's quite a lot going on in the file sticker household this morning. My son has roseola, and my wife and I have both gotten sick with whatever his secondary infection is, so things are just chaotic. We're going to do an in-class activity today. Hopefully you saw that in the announcement and downloaded the attachment. In case you haven't, let me go ahead and show you where that is. The screen should come over here. So this is the announcement. Obviously, you followed this link to get to our class meeting today. If you look down here at the bottom, there's a little link. This is an attachment. If you click this link, it will prompt you to open or save this file. Please go ahead and save a copy of that to your computer right now. We're going to work with it later. Ideally, you'll have printed this already. So if you have a printer nearby, you can go ahead and print that, but it's not necessary for today. To print it, having it printed would be nice. So if you have a printer nearby, go ahead, save it, print it. If you do not have a printer nearby, that's okay. You can work it on paper. We'll get through it. All right, that's the activity. We're going to get to that in a minute. There's a few other things we need to discuss first. Normal lecture stuff. So here we go. Now, if you find this picture in the background here interesting, by the way, then you should take pre-calculus with me. This has a really beautiful connection to factoring polynomials, believe it or not. And I will be able to explain that connection to you in detail in pre-calculus. All right. There we are. So this is MAC 1105, section 015, which is college algebra. And the date today is the 13th. Today, we're going to pick up some of the conversation that we left off with on Tuesday. Average rates of change, mins and maxes. I wanted to spend a little bit more time on that. Remember, average rate of change or average rates of change, I'll abbreviate as AROC to save writing. One other little announcement-y thing, I am going to be modifying the homework a little bit. Obviously, we're not going to get to everything that I wanted to get to today. I need to save my voice. So in my open math, where should go? Did it really close? I closed Firefox. The third homework set on linear functions includes some stuff on linear regression. Let me press it here. Oh, actually, we will. We'll get to everything in this. The linear regression is here. You just triple check. Yeah, okay, this regression thing is not going to fit in here. Everything else, I think we should be able to get to okay. So let's get to it. All right, last time. We talked about local mins and maxes. So if I have the graph of a function f here, let me go ahead and make this quite concrete. Say this point right here, it's 2, -1. Right here is 4, 3. Right here is 5, +1. Point right here is 6, 4. And this point right here is 8, 3/2. I want to also discuss globe, aka absolute ins axis. So last time we talked about what a local min or local max is. Today I want to expand that discussion a little bit to what a global or absolute max is. There's another name for local, by the way, called relative, just to clue you in on all the terminology. Here. So if you hear someone talking about a local max or a relative max, that's the same thing. If you hear someone talking about a global max or an absolute max, that's the same thing. The words local and relative are interchangeable. The words global and absolute are interchangeable. There's some specifics to the terminology here. Just to run you back through the basic idea, a local or relative min or max is a point where if you just look nearby, if you put a little window around that point, that's the lowest point anywhere in that window. So for example, here, the bottom of this valley, if I put a little window around that point, that is the lowest point anywhere in that window. So that is a local min. Similarly, here at 4, 3, if I put a little window around that point, that is the tallest point anywhere in that window. So that is a local or relative max. The way I've drawn this graph, there is a feature here that is not present on the graph we looked at last time. So recall a local, aka relative min or max is a point which is lower or taller, right? Depending on whether you're talking about a min or a max. And this would be lower. Maxes would be taller than any point nearby. And the point has to be on the graph. That should go without saying, but just to be clear, let's say it. So a local or relative min or max is a point that is lower than any point nearby. That's a local or relative min. And a local or relative max is a point that's taller than any of the points nearby. Global, aka absolute mins or maxes, are actually kind of easier to understand. A global min, global max, is just the lowest point on the graph anywhere, or the tallest point on the graph anywhere. Okay. So let's identify these points. Let's start with these guys up here. How would you describe this point? Is it a local min, local max, global min, global max? Neither. Let's add some stuff in chat. Very good. Yeah, thank you, Shady and Tyson. That is a local max, right? So if you put a little window around this guy, he's the tallest point anywhere in that window, but he's not the tallest point anywhere on the graph, right? There's taller points over here and over here. Okay, what about this fella down here, 5,1, local min, local max, global min, global max, what do we got? Excellent. Yeah, thank you, Juliana. This is a local min, right? That is the lowest point anywhere nearby, but it's not the lowest point anywhere on the graph. This would be a local max. This would be a local min. What is this point? 2, -1 over here. What is this guy?
The global min.
Very good. This is a global or absolute min. Is it also a local min?
Yeah.
Good, it's both, right? On the one hand, this is definitely the lowest point in this window. It's also the lowest point anywhere. I think I need to go take care of something. I'm so sorry. I'll be right back. Sorry about that. Smoke alarm. Okay. So local and global min. Local max, local min, local max, local min. There are some particular ways you want to describe these things. Right, there's some language that's important here, and we can connect this back to something we were talking about yesterday. If I ask, where is blank? Right, where is the min? Where is the max? You would answer blank is at the x value, right? In other words, where means at what x value. Right, and this is like we talked about yesterday with increasing and decreasing, or sorry, Tuesday with increasing and decreasing. If I ask you where is the function increasing, you tell me the interval of x values, because once you tell me the x value, that specifies the point on the graph, because the definition of a function says there's only one point associated with each x value. Similarly, if I ask you, what is, I'll just say here the min or what is the max? You would tell me the y value. Right. So if I ask you where is the absolute min for this function, you would say the absolute min for this function is at x equals 2. If I asked you what is the absolute min for this function, you would say the absolute min for this function is -1. We could say f has a local and global minimum at x equals 2. And the minimum value is -1. Right? This is how you would describe this point right here. This is a local and global min. It occurs at x equals 2. That's the location. And the min value is the y value there is -1. Right? So we're asking, like, what is the smallest output from the function f? The smallest output is -1. And when does that output occur? Where does that output occur? That output occurs when x is -2. Or sorry, when x is +2. It's just a vocabulary thing, but it is important, right? There are questions in the homework that will confuse you unless you're familiar with this standard. So anytime, the reason I phrased this part the way I did, anytime you're asked where is something, you should always give the x value, right? Not the ordered pair, definitely not the y value. Where is something always means for what input or for what x value. If I ask you what is the min or what is the max, then you give the y value. We could similarly describe what's going on at 6,4. Let's just do all of them, right? F has a local max at x equals 4. The max value is 3. Right, that's this point. So when x is equal to 4, there is a local max. The max value there is the output 3. F has a local min at x equals 5. And the min value is 1. I won't list the rest of them. There's no need to do that. Hopefully you get the idea at this point, right? Any questions about how to describe mins and maxes like this? Or how to recognize them from the graph? Okay. Then I want to turn back to average rates of change. We talked a little tiny bit about that stuff the other day. So remember that the average rate of change for a function f of x from x equals a to x equals b is this ratio, this fraction, f of b minus f of a divided by b minus a. So for example, here I have a function that's described through a table, or at least part of that function is described through a table. And I just want to find the average rate of change for that function from 1 to 3. That means the thing I'm after here. So like this is the idea, right? This is A and this is B. So what I need is f of 3 minus f of 1 divided by 3 minus 1. F of 3 I get from the table. F of 3 is 1. F of 1 I get from the table is 5. And then downstairs we have just 3 minus 1, which is 2. Remember, you cannot cancel this 3. You cannot cancel this 1. The notation upstairs, f of 3 and f of 1, has nothing to do with multiplication. That's function notation. The only thing, the only thing you can do with an expression like this is plug in here and plug in here. 1 minus 5 is -4. So this is -4 over 2, which is -2. There is a connection between average rate of change and increasing, decreasing. If your average rate of change is negative from A to B, that means overall your function was decreasing from A to B. Does not mean your function was always decreasing from A to B. Just means that overall you went down more than you went up. Conversely, if your average rate of change is positive, that means that you went up more than you went down. It doesn't mean that you only went up. So a little note on average rate of change. I'm going to state the contrapositive to those statements because they're a little bit more solid. If f is increasing on the interval AB, then the average rate of change from x equals A to x equals B is positive. And a little subnote here. Oh, no, I'll just leave it like that. If f is decreasing on AB, then the average rate of change from x equals A to x equals B is negative. Right, so if you have a function that's always increasing, or at least increasing from A to B, remember you can think of the average rate of change as the slope of the secant line. That will be a necessarily positive slope. And if your function is decreasing from the average rate of change will be negative. The fun question is, what can you say about the other direction, right? The converse to these, which is the note that I was, the kind of subnote I was tempted to add there. Is it true that if your average rate of change is positive, you must have been increasing? Not necessarily. Just means you went up more than you went down. So I'll just say, however, Just because the average rate of change is positive doesn't mean the function is increasing. This is what we call a one-way implication, right? If you're increasing the whole time, then your rate of change must be positive. But the other direction isn't true. If your rate of change is positive, that doesn't mean you're increasing the whole time. I'll show you an example here. All right, so if I look from A here to B here, this average rate of change, the slope of this dotted secant line is positive. But we're not increasing everywhere from A to B. We're increasing, decreasing, increasing. It just means we did more increasing than decreasing. And you can replace the word positive here with negative. And the word increasing here with decreasing. All right. And we can imagine a picture for that as well. Certainly my average rate of change between these 2 points is negative. But I did a lot of both. I did decreasing, increasing, decreasing, both. So it's a one-way implication. What I'd like to do now is to connect this concept of average rate of change to this classification scheme for functions. Any questions on, first let's back up a little bit. Questions on this calculation here, finding this average rate of change? Any questions on the note here? Okay. Linear functions. So sort of the simplest family of functions we can study. We're going to study many different families of functions in this class, but in some real sense, the simplest family of functions we're going to study are linear functions. The definition, there are several ways to define a linear function. Let's start with this. Function f is called linear if its graph is a straight line, single straight line. No curve, no change in direction, no turning points. You could say equivalently, function f is called linear if its average rate of change over any interval is constant. That constant is called the slope of the line. And then a third equivalent definition everybody's favorite thing from middle school. Linear functions are those that can be written as mx plus b. M here is called the slope. Is a constant. B here is called the y-intercept. So good. So kind of the more interesting definition here is the constant average rate of change. And this is the one that we use more often than not to figure out if a function given to us in a table is linear. If the function is given to you as an algebra formula, then you can use this definition. If you're given the graph, then of course you can use this definition. All three are equivalent. I'm not going to prove their equivalence to you, but I do just want to take a look at a problem or two. And I'm going to add a little bit to this. If the function is linear, I want to put it in the form y equals mx plus b. Okay. So I've described for you 3 functions here. 2 of them are given as tables. One of them is given as a graph. Let me add a 4th. All right, 4 functions now. I want you to tell me whether each one is or is not linear. If the function is linear, I want to say how you can write it in this nice form: y equals mx plus b, f of x equals mx plus b. What should I do with this first guy? Which of those 3 definitions is most useful here?
The y-intercept.
The average rate of change.
Yeah. So if you're given a function as a table, the only real way to check whether it's linear or not is to compute all the rates of change, right? You can look at the rate of change from -1 to 0, from 0 to 1, from 1 to 2. If all of those come out to the same constant, then you do have a linear function. If they do not all come out to the same constant, then you do not have a linear function. You could, in theory, also say you're going to compute -1 to 1 or 0 to 2. You can compute any combination of average rates of change there. They should all come out to the same constant. But if you're looking for a systematic way to check, just go pairwise. Do, 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 do. So what we're going to do is check the average rates of change. Right? So from x equals -1 to x equals 0, we have f of 0 minus f of -1 divided by 0 minus -1. F of 0 is 1. F of -1 is -2. So this is 1 minus -2 divided by 0 minus -1, which is 1. 1 minus -2, that's 3. So this is 3 over 1, which is just 3. From x equals 0 to x equals 1, we have f of 1 minus f of 0 over 1 minus 0. This is all. This is all for part A. F of 1 is 4, f of 0 is 1. So this is 4 minus 1 over 1 minus 0. That's also 3. So far, so good, right? From x equals 1 to x equals 2, we have f2 minus f of 1 over 2 minus 1. F of 2 is 6, f of 1 is 4. 6 minus 4 over 2 minus 1, which is 1. 6 minus 4 is 2. All right, so is the function described in part A linear or not? Good. Right, average rate of change 3, average rate of change 3, average rate of change 2. Doesn't have a constant slope. The slope changed, right? And a straight line can't have its slope change. All right, so this was all for part A. Do the same thing for part B. I'm just gonna write them out here instead of writing all the words too. So if I look first at f of 2 minus f of 1 over 2 minus 1. What do I get? F of 2 is 5. F of 1 is 7. So that's 5 minus 7. 2 minus 1 is 1. That's negative 2. If I look at f of 3 minus f of 2 over 3 minus 2. F of 3 is 3, f of 2 is 5, so that's 3 minus 5 over 1, which is also negative 2. If I look at f of 4 minus f of 3 over 4 minus 3. F of 4 is 1, f of 3 is 3, so this is 1 minus 3 over 4 minus 3 is 1. This is also negative 2. So all of the average rates of change are negative 2. This guy is linear. And we can go further. We can put this into y equals mx plus b. The challenge, of course, here is that I have not given you the y-intercept, right? So we're going to need a special tool to put this into the form y equals mx plus b. One option is to go hunting for the y-intercept. But that's way too much work. I'm lazy. And mathematicians were lazy motherfuckers. So let me share with you a secret tool. And you will need this. You'll need this in this class, and you'll need this in future classes. So the equation for a line passing through the point x0, y0, this could be any point on the line, doesn't have to be the y-intercept, is y minus y0 equals m times parentheses x minus x0. And you need to hold on to this for this is important. Right, this is like y equals mx plus b, but way more useful because you can use any point. You don't need the y-intercept. And in fact, you can use this to find the y-intercept. Right, does everybody have this down? This is your point-slope formula. You're going to need this several times throughout the semester, all the time in pre-calc, all the time in Calc 1. X0 is the x-coordinate of the point you know is on the line. Y0 is the y-coordinate of that same point, and m is the slope. X and y are the variables. So if I come back here looking at part B, we know the slope, right? Slope is the average rate of change, or the constant rate of change. It's always the same for this function. It's negative 2. I don't know the y-intercept yet, but I do know a point. In fact, I know several points. Can anybody tell me a point that is on the line in part B? Good, 1,7. Right, when x is 1, f of x is 7, so 1,7 is on the line. That means x0 is 1, y0 is 7. So now by my point slope, y minus 7 is equal to -2 times x minus 1. You could just give me this as your answer if I just said, give me the equation. But we did ask to put it in y equals mx plus b. So let's do that. This is the same as y minus 7 equals, we're just going to distribute this -2. That's -2x plus 2. And then adding 7 everywhere. We get y equals -2x plus 9. So the y-intercept here is 9. And the slope, like we said, is -2. I think part C and D I'm going to have to do on a separate sheet of paper. So for part C here, just looking at the graph, is that linear or non-linear? Good. Yeah. Because the graph is a straight line. And can you tell me the y-intercept? Very good, right? It's the y-coordinate where the line crosses the y-axis. That's -2. Can you tell me the slope? Slope here may require a little bit more thinking. I don't think it's 1. It looks like it's definitely positive, right? If the line is like, because it's going up as we go to the right. So here's how we do this. Remember, we need to calculate the rise over the run between 2 points that I know are on the line. One point that I know is on the line right here is 0, -2. I don't know what point has x coordinate 1 or any points in here for sure. It's hard to tell. The next point that I know for sure is 2, 1 over here. So I'm going to use these 2 points to calculate my slope. My rise. How much did we go up? We got 1, 2, 3. How much did we go over? 1, 2. So the slope m is the rise over the run. It's the same thing as the average rate of change, guys. It's the exact same thing, right? F of B minus F of A divided by B minus A. However you want to think about it, it's 3/2. Therefore, 3 dots arranged in a triangle like this means therefore f of x here can be written as 3/2 x minus 2. Right, I suppose I should have done that over here also. Put it in function notation, f of x equals -2x plus 9. Okay. Really quick, what about this last one? What about part D here? Linear or nonlinear? Which definition should we use? I feel like the last definition is the most useful here, right? Just can I put this in the form mx plus b? So I'm just going to try to do some algebra with it. I'm not sure what the graph of this looks like yet. I definitely don't want to plug in a bunch of numbers and try to compute average rates of change here. Let's just see if I can put it in that form. There's some algebra rules we'll use. If I have a fraction, 2 terms upstairs, I can split that shit up. It's just like having a common denominator, but backwards, right? So I can write this as 2x over 7 plus the square root of 3 over 7. And then another little algebra rule. All 3 of these are equivalent. So 2x over 7 can be written as 2/7 times x. Right? X is the same as x over 1. If you multiply 2 over 7 times x over 1, you get 2x over 7. So I can write this as 2/7 x plus the square root of 3 over 7. So I ask you again, is this a linear function or not? Yeah, very good. It is, right? Here's m x plus b. Just little baby algebra tricks here. Important things to know and be comfortable with. So yeah, this is indeed a linear function, right? And the way I discovered that is by writing it in the form mx plus b, so I don't need to go through any more bullshit there. All right, figuring out if a function's linear or not terribly hard. It just depends on how it's given to you. If it's given to you as an algebra formula, like part D here, try to massage it into mx plus b. If it's a graph, just figure out, is the graph a straight line or not? Very, very straightforward. It's given to you as a table. That's the kind of annoying one where you need to check a bunch of average rates of change and see if they're all the same. If any one of them is not the same, then it's not linear. Otherwise, it is. That point slope formula, that's a big deal. Make sure you get comfy with this. Make sure you have that in your notes. didn't write it down before, please take a screen cap here. There's one question in homework 3 that I have not equipped you to answer yet, and that's the question that has to do with linear regression. Instead of rushing this right now, I could do that. Instead of rushing this right now, I want to complete that activity. So what I'm going to do is I'm going to create some breakout rooms, and I want you guys to work on the activity questions together. I'm going to pull up the activity. We can review it really quickly. All right, the first bit of this is just about inequalities and interval notation. So I describe a bunch of sets of real numbers here, and I want you to write down the intervals that we're talking about. So can you write all real numbers as an interval? Can you write all the numbers that are bigger than 3 as an interval? Can you write all the numbers that are bigger than 1 and not bigger than 7 as an interval? All right, so on. And then similar sort of shit here. I give you some sets and I want you to sketch them on the number line. Okay, nothing crazy, just using the notation we were using the other day, where you shade, right? And then you can either use brackets and parentheses or filled in points and open points. So this first bit's just about interval notation. The second bit is about mins and maxes and increasing, decreasing. So I've got the graph of a function here. I want you to tell me where this thing is increasing and decreasing, right? So remember open intervals of x values. Tell me where this bitch is increasing and decreasing. And then finally, tell me if there are any local mins or local maxes, and are any of them absolute, or are they just local? All right. Remember, everybody should have saved a copy of this. It was in the announcement. If you did not save a copy of it, if you did not save a copy of it earlier, please do so now. It's in the announcement for today's class as an attachment. All right. So right down here, this little link, save a copy. I'm going to put you into breakout rooms. I want you guys to talk with each other. I'm going to come in and ask you some questions. You're not going to upload anything. So I'm just going to come in. I'm going to split you into breakout rooms. You guys are going to talk to each other about the problems. Make sure you come to a consensus. And then I'll come into each of the breakout rooms and talk through some of the problems with you. It's going to be an all or nothing thing. If you're here today and you guys work through the problems, you're going to get 10 out of 10 on this. So don't stress, but I am going to come in and bug you about it. So give me just 1 minute. How many people we have? We're all together 25. So I'm going to make 5 breakout rooms. That means you have 5 people in each room. When you get the invite, go ahead and join the room. Go through them problem by problem. I'll come in in a few minutes, check up on you, and then I'll come through again in another few minutes to talk to you about the answers you come up with. All righty, go ahead and join the rooms when you get the invite. Alrighty, guys, how we doing?
Working on it.
Good. Do we have any questions?
Is there a way to type the pi symbol?
I just type the letters PI usually. There is. If you can type if you know the Unicode, but there's no need. So let's just talk through a few of these problems really quick. That way I can verify that you've worked some of them. I'm going to turn on my screen share here. How would I describe? Sounds like you're talking about maybe this one, right? Where we've got a pi. Let's talk through this one. So we want all the numbers that are at least -2 and strictly less than pi. How would I describe that in interval notation?
Parenthesis -2 comma pi with the bracket sign.
Let's see. The endpoint's there, correct, but I think we have the delimiters backwards. So if we need to be at least sorry, excuse me. That means definitely stuff between -2 and pi is good. So you're correct to say that the interval is from -2 to pi. If I say I am at least as tall as Sally, that means maybe I'm taller than Sally, but also maybe I'm the same height as Sally. So at least -2 would be including -2. And for that, we would use a bracket. And then if I say I'm definitely shorter than Joe, I am smaller than Joe, that means Joe is for sure taller than me. So pi would be excluded with a parentheses. So the numbers we're talking about here are things that live between -2 and pi, possibly including -2, but not including pi. So we would have here bracket -2 comma pi parentheses. Does that make sense?
Yeah.
Okay. And then maybe somebody else from the group, just so I can verify that we're all kind of playing along a little bit together. How would I shade part E in problem 2? All the numbers smaller than 2.
It would be an open circle on 2 and then a line all the way to the left.
Very good. So that would look like 2 here. Since we have to be strictly smaller, then we don't want to include 2. So the open circle or a parentheses would be fine there, either one. And then we'd shade everything to the left because we get smaller as we go to the left. So just like that. All right. Finally, and I know it's possible we haven't gotten here yet. Can somebody tell me just one interval on which this function is definitely decreasing?
Negative infinity to -2.
I don't think that's correct. So negative infinity to -2 would be everything up to here, right? That would be saying from all the way from out here to up here, we are decreasing. It's true that we're decreasing, but then here at -4, we turn around and we're increasing, and then decreasing. So remember, we want intervals of x values. Maybe we're getting a little bit trapped up there, right? Because -2 here is a y value where we turn around. But remember, we want intervals of x values. So just one interval on which this function is for sure decreasing. Remember,
To infinity.
yeah, very good, right? X values. So 0 to infinity works. this whole portion of the graph here is decreasing, right? Going downhill as we go left to right. So that smallest x value there, that's 0. And then we continue decreasing all the way out to infinity. Okay, guys, I'm going to make a little note here to give everybody in your group 10 out of 10 for the activity. Do please continue solving the problems, though. I may bug you one more time for one of these last guys or one of these other ones. But for now, everything looks, just wrap up the rest of these, and I'll come in and check on you in one more second. Alrighty, hello, gang. I just want to come in here and check up on you, see how you're doing. Are there any problems there that you had a question on? Anything you'd like to talk about?
So for all real numbers, I just always wrote it out. Is there like an actual like symbol for it?
That's true. There is a specific symbol for all real numbers if you want to use that. In this case, we are asking for interval notation, but I'm happy to share with you. So the set all real numbers. If I want to refer to that in general, it's not uncommon to use this symbol, which is a blackboard bold R, but that's not interval notation. So how would I describe this as an interval?
Wouldn't you say R just like all real numbers equals X?
Well, remember, we're looking for something like negative infinity to 3, or 1 to infinity, something that looks like this. So something with like brackets, parentheses, and endpoints. Is there a combination of symbols like these I could use to describe the whole real line? This one might seem a little bit silly, so I don't mind just telling you. This is negative infinity to positive infinity, right? Everything. I am just going to grab one or two more of these problems and ask you guys to share your answers, just to kind of make sure we're actually participating. I don't mean to frustrate you with that. Could anybody tell me how I would write all the numbers greater than 1 and not exceeding 7 as an interval?
Would it be open parentheses, 1, and then 7, and then closing parentheses?
Very good, very good. All right, so all numbers greater than 1 and not exceeding 7. That means I'm definitely bigger than 1, and everything between 1 and 7 works. Strictly greater than 1 means 1 is not included. If I say my height is greater than Sally's height, then I'm definitely not the same height as Sally. I'm claiming that I am strictly taller. So this would be a parentheses. And then not exceeding means no larger than, but potentially equal to. If I say my height does not exceed Joe's height, that means maybe I'm shorter than Joe, but maybe I'm the same height as Joe. So 7 would be included here. So that was exactly correct. This would be the interval 1, parentheses 1, comma 7 bracket. Okay, I'm going to do just a few more of these, and I'd like somebody else to answer for me. We can jump over this. How about this? How about part E? Can somebody who has not answered me yet tell me how would I sketch all numbers smaller than 2?
Put the parentheses on the 2, and then it just goes to infinity, or negative infinity, sorry.
Good. So if I want to talk about all numbers that are smaller than 2, we put a 2 here and a parentheses like this, and then everything to the left, like that. Okay, I'm going to do just one more of these for you, please. If someone who I haven't talked to actually, tell me an interval on which this function is increasing.
-4 to 2.
Let's see. So the interval from -4 to 2 would be all the way up to here. Are we?
Or to 0, sorry.
So this is, I know it's I'm sure everybody could point to and shade the part of the graph that is increasing. The trick here is to discipline your mind to remember always intervals of x values. So the x values are from -4 to 2, right? This portion, sorry, from -4 to 0, this portion, the graph. So just remember, always, always, always x values. Anytime you're asked that, before you give your answer, stop and be like, wait, am I describing it in terms of x values? Okay, very, very good. I will go ahead and assign a 10 out of 10 to everybody in this group. I just want to check real quick. Ryan, are you with us?
Yeah, I'm here.
Okay, cool, cool, cool. Okay, I'm going to bump to the other room. Guys, please finish this up. I'm going to ask a few more questions after we're done here. I know we're going over just by a few minutes. Give me like 10 seconds and we'll wrap this up. Okay, guys, any questions on the activity problems?
Can we have help on problem 1F?
Sure.
Thank you. We're a little confused about that one.
Yeah, no stress. That's what we're here for. All right. Let me turn on my share. We can do it like this. Yeah, all real numbers except for 2 and 3. This is a tricky one. So I have a particular trick for this. First, let's sketch it on the number line. So I'll put 2 here and 3 here. I don't want 2 and 3. I do want everything else. So everything to the left of 2 is good. Everything between 2 and 3 is good. And there's a shitload of stuff in here, right? 1 is in here, but also 2.5 and 2.7 and 1.3. Sorry, not 1. No, 1 is over here. But 2.1, 2.5, 2.7, 2.9, there's lots of stuff in between. And then everything to the right here. So then I look at my shaded line and I ask, how many intervals do I have? Well, I see 1 interval, 2 intervals, 3 intervals. This is -infinity up to 2. This is 2 to 3. And this is 3 to infinity. Right? 3 separate chunks. And I use parentheses on all of these because I do not want to include 2 and 3. I'm looking for all real numbers except 2 and 3. And then the hint or the trick is that you should have the same number of union symbols as you have numbers you've removed. So if you're just kicking a few numbers out of the real number set, the number of unions is going to be equal to the number of numbers you've kicked out. So I'm just punching out 2 numbers. I should have 2 unions, 1 for each of those. Does that make sense? The thing people mess up here is they forget about the stuff between 2 and 3. Everybody forgets this interval. So sketch it, sketch it on the number line, and that will help you a lot.
Thank you.
Of course, before I let you guys go, I do want to just check up on a few other ones here. Can anybody tell me, how do I shade all numbers smaller than 2?
Would it be the open circle on 2 and then everything to the left of it?
Very good. Yeah, very good. All right. And then I'll ask maybe somebody other than Elena, could you tell me an interval on which this function is increasing?
-4, commas.
Oh, I heard it, -4, comma.
0.
Very good, very good. And it's the x values. That's excellent, Tyson. Thank you. Can anybody tell me a local max for this function? Someone other than Elena or Tyson, please.
I was gonna ask, the arrows just keep going down, right, as infinity?
Yeah, this one keeps going down forever. and this one keeps going up forever. So there's not going to be any global max or global min. This one keeps going up, 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 and this one keeps going down, 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 down. But can we identify a local max?
2.
2 would be the max value. And where is that local max? What's the location?
0, 2.
Good. So we would say there's a local max at x equals 0, right? And the max value is 2. That's wonderful. All right, thank you guys. Continue wrapping these up, and I'll bring everybody back into the main session in just 1 second. Okay, guys, we're almost done here. I just wanted to check and see if anybody had any questions on the activity.
We finished, but a couple of them we're not completely sure about.
Okay, which ones were we unsure about?
I think
So
C,
on-
right?
Yeah, on C, when it says not exceeding, does that mean not exceeding but including, or?
It does, yeah.
That's what
So
I
if I were to
thought.
say
So
that
there's a
the-
bracket.
Yes, exactly. So this is parentheses 1, 7 bracket. That would be C here.
Okay, and then F, there's a union involved, right?
Yeah, this is the good one, right? So everybody makes a little mistake on this one. In fact, I have it ready here. So let me reveal this gently. So we want all real numbers except for 2 and 3. My advice here, shade the set. Shade the set. So we draw the real number line, right? And here's 2, here's 3. I want everything except 2 and 3. So that means everything to the left of 2 is good. Everything between 2 and 3 is good. And there is a lot of stuff in here, right? Like 2.5, 2.1, 2.9. There's a lot of stuff in here. Don't forget this stuff. And then everything to the right of 3 is good as well. I have a little trick for this. The number of unions is equal to the number of numbers you've kicked out. So you see here, I've got one interval. This is the interval from -infinity to 2. Got a second interval here. This is the interval from 2 to 3. And then I have a third interval here. This is the interval from 3 to infinity. So I'm going to union those 3 intervals together. -infinity to 2, 2 to 3, and 3 to infinity. And you see for each of these guys that we punched out, we get a union symbol. So if you wanted to shade this using the notation we've used in class, it would look like this.
Thank you.
People forget, everybody seems to forget this middle guy, so watch out for him. The safe way to do that is to sketch it on the number line. All right, just as a kind of verification before I wrap things up here, could somebody, maybe somebody I haven't heard from yet, tell me an interval on which this function is increasing?
Isn't it increasing -4 to 0?
Very good, yeah, right? This is the portion of the graph that is increasing, and the interval of x values there is from -4 up to 0. That's perfect. All right, thank you, Emma. I'm going to go ahead and bring everybody back into the main room. And then
being recorded.
alrighty, gang. So we are coming back into the main session. There was one problem in that I think probably everybody needed a little bit of extra thinking to get through. Most of us did really well with the increasing, decreasing. Just remember to give me intervals of x values. So this function is increasing from -4 to 0. It is decreasing from -infinity up to, decreasing from -infinity up to -4, and from 0 to +infinity. There is a local min at -4, and the min value there is -2. There is a local max at 0, and the max value is +2. Among these, the one that seems to give folks the most trouble is part D in problem, part F in problem 1. So I just wanted to talk about that for a second, then I'll let you guys go. We're looking for all real numbers except for 2 and 3. The trick to this is to shade the thing on the number line, right? So I know I don't want 2 and I don't want 3. That means everything to the left of 2 is good, everything between 2 and 3 is good, and everything to the right of 3 is good. The trick here is that if you're just removing a few isolated numbers from the number line, you should have the same number of union symbols as you have numbers you have removed. So I see here 3 intervals, this interval, and this interval. And I union those 3. That's negative infinity up to 2, 2 to 3, and 3 to infinity. And you see for each number I've punched out, there is a union symbol. The thing people forget is the interval 2 to 3, right? Everybody forgets this. So just be mindful of that. If you're trying to graph a set of numbers on the number line or write a set of numbers in interval notation, first graph it on the number line if there's any uncertainty. There are infinitely many numbers between 2 and 3. 2.1, 2.2, 2.3, 2.4, 2.5, 2.6, 2.73, 2.99, right? There's infinitely many numbers in here. Don't forget these guys. Okay, I'm going to give everybody who was in the breakout rooms there 10 out of 10 on the activity. Thank you guys for hanging around. There is that one regression problem on homework 3. Don't worry about that. Go ahead and do everything else, so please. And I will work out the stuff in MOM. Next week, we will talk about regression and applications of linear functions. But for now, this is everything we should need to get through homework 3. If you do get stuck on anything, you can come see me in office hours, or you can send me a Canvas message. If you've got to go, you got to go. I understand it's 11 o'clock. Today's office hour is going to be an exception, though. I'm sick as shit. My voice is totally shot. So I am going to cancel today's office hour. I'll have my normal one tomorrow from 1 to 2. And of course, I'll be responding to emails and Canvas messages. That's it from me, guys. Please do wrap up homework 3, except for that regression problem. If you're stuck on anything, ask for help. And I'll see you next Tuesday.